Good morning everyone. Last time we have discussed about the nucleophilic substitution reaction, especially the mechanism that is SN2 mechanism, substitution nucleophilic bimolecular. And this time we are going to discuss about the SN1 reaction mechanism, that is the substitution nucleophilic monomolecular, unimolecular. So when you will see the reaction will be same as it was in the previous case. That will be CH3Cl. When reacts with KOH, it gives CH3OH plus KCl. The same reaction whatever we have taken in the previous case. Now when you will see for this reaction, the mechanism says that the condition must be a protic solvent, and in presence of protic solvent the KOH will break in the form of K plus and OH minus. Even in the absence of protic solvent it can break in the form, because the KOH is a very strong electrolyte. But when you will see the condition of the substrate, that is the CH3Cl chloromethane, the CH3Cl will also break in the form of the CH3 positive and Cl negative. That means it will form the carbocation, and it is due to the protic nature of the solvent. Now this carbocation will again approach the nucleophile, that is the hydroxyl ion, and after approaching it will form methanol. Now this remaining chloride ion will approach to the potassium and it will form KCl. In this mechanism, the first step, that means this step, is a slow step, and the second step is surely or respectively fast step. And as this step is a slow step containing just a single molecule, so the reaction is a unimolecular. Only one molecule is determining the rate of reaction, so it is a unimolecular reaction, as it is already written substitution nucleophilic unimolecular. Now when you will see the steps, in the previous case I have said that the intermediate is highly unstable, and being highly unstable the system was running in a single step, or the reaction was running in the single step, and it was considered. But here in this case the intermediate is a carbocation, which is much stable than the pentavalent intermediate. It can be recognized, it can be easily identified, and this is the reason why we say the reaction is a double step reaction. So there are two steps in this reaction. The first step is the fast reaction, that is the rate determining step, and the second step is the slow step, that is the non-rate determining step. Now the last one, when you will see whether the system is going for the retention or inversion, whether that is retaining their integral configuration or that is changing. When you will see in the reaction, the chlorine is on my right hand side, and similarly the hydroxyl is again on my right hand side. So it seems that retention is taking place. As it is showing, the reaction is showing, it is saying that the retention in configuration is taking place, because the chlorine group was on the right hand side, and similarly the hydroxyl group is also on the right hand side. But when you will see the actual condition, what appears? We say when we provide a charge to a hollow sphere, that means a sphere which is vacant, to a hollow sphere, the charge disperses over the surface of the system, over the surface of the sphere. What will be the condition here? When you will see the condition of an atom, there is a small nucleus in the center and electron rotates around it. That means the system is just like a vacant sphere. And if it is just like the vacant sphere, the charge will disperse over the surface of the system, So if this is the atom, this is the carbon which is containing the charge will be somewhere here. That means everywhere on the surface of the system. So from which of the side the hydroxyl group will approach, whether it will approach from the front or the back, there's 50-50 chance of approaching from the front as well as approaching from the back. And this is the reason in this type of the mechanism no retention is obtained, it is the racemization. That means the 50% retention and 50% inversion takes place. So the racemization process takes place in the case of the SN1 reaction mechanism. So what are the criteria? It is a unimolecular reaction or double step reaction. It undergo the process with the racemic product racemization, even some retention product is also obtained. So this is the general criteria of the SN1 reaction, that is substitution nucleophilic unimolecular. Now we are going to see the rate of reaction for the SN1. In the previous one, that is the SN2 reaction, we have discussed the rate of reaction, and then I have said that the rate of reaction can be determined on the basis of the stability of the carbocation. But there we haven't seen it on the basis of the stability of the intermediate, because the intermediate was so unstable that its stability was not determining the rate of reaction. But in this case, in the case of the SN1 reaction, the intermediate is stable, and as the intermediates are stable, so with the stable intermediate, the system will determine their rate with the stability of the intermediate. If the intermediate is more stable, the rate of reaction will be greater, and if the intermediate is less stable, surely the rate of reaction will be slower. So we are going to study the rate of reaction in the case of SN1 on the basis of the stability of the carbocation. So we are going to see the rate of reaction in the SN1, and here are the carbocations which is generated in the different case. The carbocation, that is the methyl carbocation, primary carbocation, secondary carbocation, and the tertiary carbocation. We are just going to discuss about the stability. Even you know about the stability of these of the carbocation. In the last year we have discussed when we were studying about the inductive effect. So when you will see the methyl carbocation, the first one, you can see that 3 hydrogens are attached with the carbon. This carbon is common, this positive charge is common. So we are not going to discuss about these two things, that is the carbon on which the positive charge is there and the nature of the positive charge. So in these of the 3 attachment, that is the 3 hydrogen, what will be the effect on the charge? There will be no effect, because hydrogen is neither donor nor the acceptor of the electron. So whatever the charge here, that must remain same. But when you will see the condition of the primary system, there is a alkyl group along with 2 hydrogens, and this alkyl group is a well known electron donating species, or you can say that generates a plus I effect. Having plus I effect, having the electron donating effect, the charge density on the carbon will decrease, and with the decreased charge density, the system will become more stable, the carbocation will become more stable. So this carbocation is much more stable than the previous one. So this is the stability. What's about the next one? What's about secondary carbocation? This one have 1, 2 alkyl group, that means 2 donor groups. Having 2 donor group must have the greater charge density. Having greater charge density, the system will be lesser charge density, the system will be more stable. 2 alkyl groups are donating greater number of electrons, that is decreasing the charge density on the carbon. So the carbocation will become even more stable than the primary one. So the secondary carbocation is more stable than the primary, and similarly the tertiary is more stable than the secondary. And the carbocation stabilities are suggesting the rate of reaction. So when you will see the rate of reaction, it will be maximum in the case of the methyl, then primary, secondary, and tertiary. When you will talk about the aryl system, they are the least stable, because in the case of aryl system, there is no chance for the generation of the carbocation, because the aryl carbocations are highly unstable. So, highly unstable aryl carbocations are not capable to give the proper rate of reaction in the case of the SN1, and this is the reason the substitution nucleophilic, whether it is the SN1 or the SN2, is the slowest in the case of the aryl system. But if you are taking the same alkyl group, methyl, ethyl, propyl, primary, secondary, tertiary, whatever it is, the same alkyl group with a different halogen, that means bromine, chlorine, bromine, iodine, then what will be the rate of reaction in these of the cases? Which one will go faster rate of reaction? You can say that with the same alkyl group, the iodine will undergo the faster, iodides will go faster reaction, then it will be bromo compound, chloro compound and fluoro compounds. Why? Due to the cleavage property. Iodine have the greater bond length, having greater cleavage property, whereas chlorine and bromine have the smaller size, smaller radius, having a smaller bond length, so they have the smaller cleavage property. And this is the reason, this is the rate of reaction in the case of the SN1 reaction. I think it's clear to all of you. In the next video, we will discuss about the elimination reaction and some of the other properties of the haloarene. Till then, bye. Have a nice day.